Hello everyone, welcome back. My name is James Apanda, your private tutor for understanding electricity. Previously, we saw that a transistor can act as a simple switch. It's either on or off. But today, let's take a step further. What if we don't just want on or off, but we want to make a small signal stronger? That is where the transistor becomes an amplifier. Here is the idea. When we apply a tiny input signal to the base of a transistor, it allows a much bigger current to flow through the collector. And that bigger current creates a much larger output voltage across the collector resistor. In other words, the small input signal at the base of the transistor appears at the output but amplified. But there's a catch. If we just connect the transistor without any preparation, it either stays completely off or goes into distortion. So what do? We bias it. Yes, we bias the transistor. Here, biasing simply means we set up the transistor at a comfortable resting point so it's ready to respond to signals both ways. Now consider this full common emitter amplifier. Resistors R1 and 2 form a potential divider network to give the base the right DC level. Resistor RE stabilizes the circuit. Resistor RC helps to convert changes in current into changes in voltage. Capacitor C1 and capacitor C2 are coupling capacitors, which allows only AC signals to flow whilst blocking DC signals. So the transistor sits in the active region and now it can properly amplify. So here we are with the constructed amplifier, and we've constructed it on the breadboard. We want to measure the DC values across the resistors and also across the terminals of the transistor. This will help us to know how well this amplifier would perform. So this is the circuit diagram. We have R1 and R2 forming a potential divider network across the power supply VCC. And then we have the collector resistor RC. We have the emitter resistor RE, and then we have the transistor, which connects to all the resistors that have been mentioned. We also have the capacitors, but we don't have the capacitors on the circuit here because we are not going to consider AC analysis. We are only considering DC analysis. So let's power it up and then test this amplifier. Now, these are the various test points that we shall be looking at. So looking at VCC, we're looking at VR1, VR2, VB, VRE, VRC, VCC, and then VC. Okay. So let's power the multimeter and set it to voltage range, since we are going to be measuring voltage. So we turn it on and it is already on voltage, but we need to make sure it is on DC. So as you can see, it's already on DC. So we are good to go. Let's power it up. We're powering it up with the 9 volts battery. So let's go. So we have 9.09 volts. So let's record this value, 9.09. Let's measure the voltage across R1. This is R1. So we want to measure the voltage across it. So there we go. We just place the meter terminals, the test leads across R1, and there you go, you see the voltage 8.27. So let's record that one as well. 8.27. We have VR1, which is 0.81 volts. So 0.81, 0.81. Then next we have VB. So the voltage between the base and the emitter, that is from here to here. So this is what we're going to do. Just place the red test lead on the base and then the black test lead on the emitter. So this is the base of the transistor and this is the emitter of the transistor. So we have 0.613 volt, 0.613, 0.61. And then the next one is VRE. So the emitter resistor, we're going to measure the voltage across the emitter resistor. So we locate the emitter. This is the emitter of the transistor. And then the black test lead will be on 0 volts, the ground. Okay, so, or you simply place the test leads across the emitter resistor. So here we go. Well, 0.197, let's say 0.2 volts, 0.20, and then VRC, the voltage across this collector resistor. So we also place our red test lead on the positive line and then the black one on the collector of the transistor. This gives us 4.22 volts. 4.22 volts. And we have the VCE, which is the voltage between the collector and the emitter. So with this one too, we place the red test lead on the collector and the black test lead on the emitter. That's exactly what we're going to do. This is the collector and this is the emitter. And this is giving us 4.67 volts. 4.67 volts. So let's record that one too. 4.67 volts. And then finally we have the collector voltage. So the collector voltage is measured between the ground and then the collector. So we locate the collector. This is, once again, this is the collector and this is the ground. So let's take the measurement. 4.87 volts. 4.87 volts. Now remember, I said that R1 and R2 form a potential divider network. That means that the VCC is divided between R1 and R2. So if we measure the voltage across R1 and we measure the voltage across R2 and we put them together, it should give us the value of VCC. So in this case, we had 8.27 for R1 and then 0.81 for R2. So let's sum them up and see what we have. So we have 8.27 plus 0.81. This gives us 9.08, which is approximately the same value we have here. Let's also look at the voltages across RC, VCE, and then RE and C. Because when we sum that 1, 2 up, we shall have the VCC. So let's sum them up. We have VRC, which is 4.22 plus VCE, which is 4.67, and then finally the voltage across the emitter resistor, which is VRE, that is 0.2, so 0.2, and this gives us 9.09, which is the same as VCC. So that is these are the parameters. Also, we need to look at the output voltage. Now, the output voltage corresponds to the voltage across the collector. So VC, this is the output voltage. Now, this means that the output voltage is about half of the power supply. And this means that the amplifier is actually performing very well. It is sitting in the middle of VCC. This means that we can always have the output voltage swinging for almost half of the power supply in the positive and negative direction. So we can have up to about half of the power supply for negative, and then up to about half of the power supply for positive. So that is a very, very good indication that this amplifier can work properly. Now, let's look at other parameters as well. The voltage across the collector resistor is 4.22. So this figure is actually enabling us to have this value. If this were to be very high, this figure would have reduced, and that wouldn't be good since we are using this for an amplifier. And if it is too low too, it wouldn't be good. It has to set somewhere almost in the middle of VCC. Okay. Imagine whispering into a microphone. The sound is too weak to hear directly, but when a transistor amplifies the weak electrical signal, suddenly you can hear it clear through a loudspeaker. That is exactly what this circuit does. So, a transistor isn't just a switch. With proper biasing, it becomes an amplifier, one of the most important blocks in all of electronics. Next time, we'll dive into the design and calculation of these amplifiers step by step. Thank you very much for watching this video. See you soon.